start this video with kind of going back a little bit, just reviewing the general forms of energy, and then we'll clarify a little bit how we express that energy with units of joules or calories. Again, as you know, energy can be either kinetic, something's moving has kinetic energy, or something has potential energy because of its position. But regardless of that, we have generally broken all the different forms of energy that we experience on Earth into 7 forms. Mechanical energy, car engines, bicycles, roller coasters, sound energy. Bats use sound waves to navigate because their sight is very bad. Music, animals in the ocean use sound waves to navigate. But sound is just a form of energy expressed using waves to move through the environment. And then we have chemical energy, which we're most interested in. The energy stored in bonds that's released in reactions. There's electrical energy, so batteries, bolts of lightning carry tremendous amounts of electrical energy. There's light energy. Ultimately, all energy on Earth comes from light energy from the sun and stars. Heat energy, which is just the movement of particles. The faster they move, the hotter they are. The slower they move, the cooler they are. Heat energy is sometimes called thermal energy. And then we have nuclear energy, which is released in atomic bombs and hydrogen bombs and used in nuclear power plants. So I also want to review the units that we use to express energy. So what are they? Well, we have joules and calories. In Europe, they use the unit of joules, capital Joules. The joule was named in honor of James Prescott Joule, who was a physicist and brewer. And in the United States, we use calories, as you know. But if you ever took physics, you probably learned that a joule is defined in units of Newton meters. Now, I know this is not a physics class, so don't worry too much if you're not grasping this, but I just want you to know where these units come from. Now, a joule, again, is a unit of energy, which also can be considered work. A work, in the simplest sense, is a force applied through a distance. So the unit of force in physics is called a Newton, after Sir Isaac Newton. And a Newton is defined as the amount of force you have to give to 1 kilogram to accelerate it at 1 meter per second squared. So another way to look at that would be as if you pushed a box, let's say, across a surface that didn't have any friction, but you pushed on it with a force of 1 Newton through a distance of 1 meter, you would have given that box a force or a amount of energy of 1 joule. Examples of 1 joule, to give you some sort of idea of what that is, it's actually a very, very small amount of energy. If you just take a typical apple that weighs about 100 grams and you lift it 1 meter off a table, about 3 feet up, you've just applied 1 joule of energy to that apple. And if you drop the apple, it will give the table it hits 1 joule of energy. And that's the law of conservation of energy. You can't create or destroy energy, you just convert it from one form to another. 1 joule is also the heat required to raise 1 gram of water's temperature by about 1/4 of a degree. And that's not much, so a joule can be the amount of electricity needed to light a 1 watt LED light, a real small LED, for about 1 second. So it's really, really, really a small number. That's why when we do some problems later on, you'll see the answers are often expressed in kilojoules, because there's a tremendous amount of energy. A lot of joules are released in a chemical reaction, so we express that with kilojoules, or, as you saw in the last video, kilocalories. So what's a calorie? Well, a calorie is just about 4 times as big as a joule. A calorie is really specifically 4.184 joules. Now, the calorie that you've seen on a label of food, for instance, is not this little lowercase c calorie. It's called a nutritional calorie, and a nutritional calorie is actually equal to 1,000 of these little calories, which we sometimes call a kilocalorie. So a typical apple contains about 95 calories. I put that in quotes because it's actually 95 calories with a capital C. That's a nutritional calorie. So that actually contains 95,000 calories. The physics definition of a calorie is the amount of heat you have to add to raise the temperature of 1 gram of water by 1 degrees Celsius. So that's a nice definition. We can kind of get a grasp on that. 1 gram of water is a very tiny amount of water. But that's what joules and calories are. And for instance, we can calculate. I can show you a very easy way to calculate the amount of the calorie content of food. So let's just take a Big Mac. Looks pretty good. But if you looked at the nutrition label of a Big Mac, you would see this looks like a typical nutrition label. You see the calorie content, the fat content, cholesterol, carbohydrates, proteins, things like that. Where do they come up with this 540 number? Well, it's actually pretty simple. What they do is they figured out that when you burn 1 gram of fat biochemically, it takes about 9 calories of energy. Now remember, these are the big calories, so that's actually 9,000 little calories. That's a food calorie. So if you have 29 grams of fat in the Big Mac, that's 29 times 9, or 261 calories from fat. And so they really just break it down into 3 groups to calculate the total calorie count: the fat content, the carbohydrates, and the proteins. Carbohydrates take up a little bit, they require a little bit less energy to metabolize. So for every 1 gram of carbohydrate, it only takes 4 calories to metabolize that. So if you have 45 grams of carbohydrate in the Big Mac, that's 45 times 4, or 180 calories for the calorie content just from carbohydrates. And then finally, you take the protein content, which in this case is 25 grams. And protein also requires 4 calories per gram to metabolize. So 25 times 4 is 100. So if you add up 100 calories, 180, and 261, you come up with 541. Well, food companies don't have to be that precise when they tell you, they round things off. So that's why they just round it off to 2 significant figures, 540 calories. And remember, these calories that you see here are actually nutritional calories. So a Big Mac actually contains 541,000 calories. And that sounds like a big number, but it isn't really in the grand scheme of things, because a calorie is such a small amount of energy transfer. You might have noticed that fat takes over 2 times the amount of energy to break down or to metabolize than carbohydrates or proteins. That's why we're always told to limit the fat content in our food, because fat is a high energy molecule. It takes a lot of energy to break it down. So going back to our notes, those handouts were not in your notes, but you can pause the video and catch up if you'd like. But remember, last time we were talking about reactions and how we can calculate the heat of a reaction. Either it's going to be consumed in an endothermic reaction or produced in an exothermic reaction. So I want to just give you a visual of what exothermic and endothermic are. So I'll put that aside for a second here. Let's look at an exothermic reaction. So here is it's called a reaction diagram, or sometimes they call it an energy profile. But what it shows visually is just the difference in energy between reactants and products. So this would be the energy or the reaction that occurs when you use a Bunsen burner in the laboratory. Methane gas is coming out. You burn it in the air, so the oxygen reacts with the methane, and you release CO2 and water into the environment. Typical combustion reaction. However, you know that a Bunsen burner gives off a lot of heat, so that's how we would express the heat that's given off. We use this way to represent that heat is released. So it's a little confusing for beginning students to get this, but the energy of the so an exothermic reaction means that the energy of the reactants is at a higher energy than the energy of the products. So we often represent the progress of the reaction with this sort of roller coaster looking diagram. All it really shows is that the reactants are at some energy. They need a certain amount of what's called the activation energy. So it would be like lighting a match on the methane to get it going. Once it goes, like a roller coaster, once you're over the top of the hill, you go. That's the way reactions work. Once you give them enough energy to reach this point, they will go on to products, in this case CO2 and water. Now this isn't balanced, but it doesn't really matter. I'm just showing you that the products are much more stable. So when you have something that's lower in energy, this is energy, this is just time, as time progresses. If the products are at a lower energy, they're more stable. So the reaction wants to generally go in that direction where you're going from to a more stable system. So in chemistry and physics, we say that energy is released, and the amount of energy that's released is the difference between where the products ended up and where the reactants started. And I've just shown that here in red. It's just this amount of energy, which we call delta H, the enthalpy of the reaction. Remember, that's spelled E-N-T-H-A-L-P-Y, enthalpy. In this case, delta H is less than 0. And like I showed you in the last video for that one combustion reaction, this is where the energy is coming from. The energy of the reactants, you have 4 carbon-hydrogen bonds and 2 oxygen-oxygen double bonds are breaking. So this is actually balanced. It takes 2 oxygens to react with 1 methane to give you 1 CO2 molecule and 2 water molecules. So the energy of these 2 carbon-oxygen double bonds and 4 hydrogen-oxygen single bonds is lower than the energy here. So that's where the energy, the law of conservation energy says, where does that energy go? It comes out to us as heat. That's called an exothermic reaction. In contrast to that, you can reverse that reaction. So a very well-known endothermic reaction, notice endo, E-N-D-O, the prefix means energy must go in to the system. Here in this reaction, energy came out to us. It was released to us, so we have a negative delta H. In an endothermic reaction, you have a positive value of delta H, so energy must be added into the reactants to get them to move on to products. So you can see it's just sort of the mirror image of an exothermic reaction. In this case, you have the 6 carbon dioxide molecules reacting with 6 water molecules, essentially rain. This is how photosynthesis happens. And it has to absorb about 678,000 calories of energy to produce 1 glucose molecule and actually 6 oxygen molecules. Sorry if my diagrams aren't that clear. I hand wrote all these things. But this is the balanced reaction. And you can see that energy must be added in. This is just the opposite of an exothermic reaction. This reaction still will occur with the right amount of sunlight. That's why things stop growing in the winter. The temperature is lower, there's not as much sunlight, so this reaction doesn't have enough energy to go, essentially. That's why things stop growing in the winter time. But that's the difference between exothermic and endothermic.